Hello everyone. So this is the second hour of our electrostatic and gravitation series. In this hour, we are going to talk about field. Field is a vector quantity. So when you play with field, you have to be a little bit cautious that you have to do vectorial addition and vectorial subtraction. By the way, in the next hour, we will start with potential. Potential is a scalar quantity. That's why way easier to deal with. So this is an important hour. Here you have to focus on field both because of gravitation as well as electrostatic. So without wasting time, let's start talking about fields. So first, what is field? First of all, let's talk about gravitation. So the gravitational field, the symbol I will use for gravitational field intensity will be I, and you can see here we have denoted a vector notation to it. Why? Because field is a vector quantity. Now, if we have a mass m1 and we have a mass m2 separated by a distance r, we know that there is a force of gravitation between these two masses, and this force is equals to gm1 m2 upon r square, right? But how does one mass applies force on the other mass? So we say that the mass m1 produces a field at position of mass m2. Once more, the mass m1 produces a field at the position of mass m2, and that field applies the force on mass m2. So if you have a mass, the mass produces a field in the three-dimensional space around it. Now this field, whenever interacts with another mass, a force acts on the other mass. In the diagram I have just drawn, I have taken the direction of field wrong. I will tell you that the direction of field due to a mass is towards itself. Let's understand it how. We say that if a mass m is placed at a place where the gravitational field intensity is I, then the force acting on the mass is given by mass times the gravitational field intensity at the point. So let's say at this random point P in space, we have got a gravitational field intensity I this way. So if we place a mass m here, then the force experienced by the mass equals to mass times the gravitational field intensity. Tell me, can mass of a body ever be negative? No, sir. The change in mass can be negative, but the mass of a body can't be negative. Since mass can't be negative, this quantity right here is a positive scalar. Positive scalar. Hence, we can say that the force vector in case of gravitation always act in direction of gravitational field intensity. So gravitational force always act in direction of gravitational field intensity, as this mass being multiplied here is a positive scalar. Now this force represents what? So this is the force on a mass m placed at a place where the gravitational field intensity is I. So if at a particular point the gravitational field intensity is I, then if you place a mass m here, the gravitational force acting on the mass is nothing but the mass times the gravitational field intensity. Similarly, we can define electric field intensity, or as a matter of fact we should call here electrostatic field intensity. Why? Because there are two types of electric fields, one produced by charge, another produced by time varying magnetic field. The type of electric field we are discussing here is the one produced by the charge. So if we have a charge q1 and we have got another charge q2 separated by distance r, we know that there is a Coulombic force acting between them given by kq1 q2 upon r square. But the bigger question is, how does one charge apply force on another charge? So we say the charge q1 produces a field at the position on charge q2, and that field applies a force on q2. So the charge q1 produces a field at position of charge q2, and that field applies a force on the charge q2. Now again the same type of formula we get. We say that the force acting on a charge q placed at a place where the electric field intensity is E is given by QP. Now understand that the mass is always positive, but the charge can be positive as well as negative. So can we say that electric force always act in direction of electric field? No. Electric force will act in direction of electric field or in the opposite direction depending upon the nature of charge. If the charge is positive, then we say that the direction of force and electric field will be same. But if the charge is negative, then the direction of force will be in direction opposite to the electric field. Like if we have got electric field, let's say towards right. and we have got a positive charge as well as a negative charge. The force on the positive charge will come out to be in direction of electric field, while the force on the negative charge will be in direction opposite to the electric field. Why? F equals to QE. If Q is negative, then the force vector is anti-parallel to the electric field vector. So, the force by electric field is in direction of field or opposite depending upon the sign of Q. If Q is positive, then the force is in direction of field. If Q is negative, then the force is in direction opposite to the electric field. Keep this simple thing in mind. Many a time in question you will find there is an electron moving. So remember that the force on electron is in direction opposite to the electric field. The gravitation force is in direction of gravitational field always. Why? Because mass can't be negative. Mass is always positive. Hence the gravitational force is always in direction of gravitational field, while electric force will be in direction of electric field or in the opposite direction depending upon the sign of Q. Moving on. How do we write the gravitational field due to a mass? So if you have got a mass m and you need to write the gravitational field due to this mass m at a distance r, how will you write? So we have just learned that every mass produces a field in the space in its surrounding, and whenever we place another mass in that field, that another mass experiences a force. So if we have a mass m, what is the strength of gravitational field produced by this mass m at a distance r? To find this, we place a test mass at distance r. So to find the field due to mass m at a distance r, place a test mass at distance r from the mass m. Place the test mass at the place where you wish to find the field due to mass m. Now if we place here a test mass m dash, gravitational force will act on this test mass. The gravitational force applied by this mass m on this test mass will be g m dash by r square. Yes sir. And we know that the gravitational force acting on this test mass has to be nothing but its test mass times the gravitational field intensity. So we can equate these two and write the force of gravity acting on the test mass should be equals to the mass of the test mass multiplied by the gravitational field intensity at that point. If we cancel out m dash both the side, we get that the gravitational field intensity at this point where we have placed the test mass is nothing but g into the mass producing the field upon r square. So that's how we get the field due to a mass at a distance r from it. So the force applied by this mass on test mass will be g m dash by r square, and this force has to be equals to the test mass times the field intensity. Hence we get the field intensity to be equals to gm by r square. Now tell me kids, gravitational field intensity is a scalar quantity or vector quantity? Vector quantity. Can you tell me in which direction is the field produced by this mass? So sir, we know that on the test mass, the direction of force will be same as that of field. For gravitation, the direction of force is always same as that of field. Hence, this mass must be producing a field towards itself, such that when we multiply the test mass with the field, we get the force in the direction of field. So remember that the direction of field is towards the mass. So a mass produces gravitational field towards itself. Once more, the gravitational field produced by a mass m at distance r is given by gm by r square, and the field is a vector quantity, so you should know direction as well. The direction of field produced by a mass is towards the mass. So every mass in space produces a field towards itself, not away from itself. One more thing, the field is directly proportional to mass. So if you double the mass, make it 2 times, the field at this point becomes 2 times. If you triple the mass, the field at this point becomes 3 times. If you make the mass 10 times, the field at this point becomes 10 times stronger. Moreover, the field is inversely proportional to r square. So if you think of a point at double the distance 2r, as the field is proportional to 1 by r square, you will say on doubling the distance, the field strength becomes 1/4. So if at distance r the field strength is I, then at distance 2r the field strength will be I by 4. At a distance 3r the field strength will be I by 9, and so on. So the field strength is inversely proportional to r square. So on doubling the distance, the field strength becomes 1/4. On tripling the distance, the field strength becomes 1/9. Now we will do the same talk but about charge. So, electric field due to a point charge. If you have a point charge q and you wish to write the electric field because of this point charge q at distance r, what to do? The same thing. To determine the strength of gravitational field at a point, you place a test mass. To determine the strength of electric field at a point, you place a test charge. So, place a test charge q dash at distance r. If we place here a test charge q dash, assuming both the charges to be positive, we know that the charge q will repel this charge q dash and the force acting will be kq dash upon r square. And this force kq dash upon r square also have to be equal to the charge times the field intensity at the position of charge. So from here you can see, if you cancel out q dash, E comes out to be kq by r square. So the gravitational field produced by a mass m at distance r is given by gm by r square. The electric field produced by a charge q at distance r is given by kq by r square. So the force acting on the test charge will be kq dash upon r square, and this has to be equals to the test charge times the electric field intensity. Hence we get the electric field intensity to be kq upon r square. One more time, electric field is dash quantity, scalar or vector. It's a vector quantity. So every time you are playing with field, you have to be cautious that you have to do vector addition. Now the electric field due to a charge q is equals to kq by r square. Now understand that if you have a positive charge, then it will produce field away from it. And if you have a negative charge, it will produce field towards it. So a positive charge produces field away from it, while a negative charge produces field towards it. So if you have got a positive charge, it will produce field away from it. And if you have got a negative charge, then at all points in space, it will produce field towards it. So if you place any test charge, positive test charge, the direction of force on the positive test charge is same as that of field. The direction of force on a positive test charge is same as the direction of field, right? F equals to QE. So if I take the test charge as positive, then the direction of force and field is same. If you place here a positive test charge, then the positive charge repels it. So the force is away from it. So the field has to be away from it. If you have got a negative charge, then on the positive test charge, the force will be attractive towards the negative charge. Hence the field has to be towards the negative charge. So a positive charge produces field away from it, while a negative charge produces field towards it. Moving on. How to write the field in vector form? So first we will talk about gravitational field, then we will talk about electric field. So how to write gravitational field in the vector form? If you have got a mass m and you wish to write the gravitational field because of it at a position vector r. First question, the gravitational field produced by this mass will be towards it or away from it? Gravitational forces are always attractive in nature. The gravitational field produced by a mass is always towards it. So tell me, the direction of gravitational field is parallel to r or anti-parallel to r? The direction of gravitational field will be parallel to r or anti-parallel to r. So you will say the direction of gravitational field will be anti-parallel to r. We know that the strength of this gravitational field will be gm upon magnitude of r whole square. And the direction has to be same as that of minus r. So we will multiply with a unit vector in direction of minus r. And that's how we write the gravitational field in vector format. So we will say that the magnitude of field intensity equals to gm upon magnitude of r whole square. And the direction has to be same as that of vector minus r. So we will get the gravitational field intensity in vector form as gm upon magnitude of r whole square multiplied by a unit vector in direction of minus vector r. A unit vector in direction of minus vector r will be written as minus times vector r upon magnitude of vector r. A unit vector in direction of minus r will be written as vector minus r upon magnitude of minus r, which is same as the magnitude of plus r. So you will get the gravitational field intensity in vector form to be gm upon r cube into vector r, and there is a minus sign. Why minus sign? The minus sign tells us that the gravitational field produced by a mass is always towards itself, opposite to the direction of r. Similarly, how do we write the electric field at a point in the vector form? So if you have a charge q and at distance r, if you take the charge q as positive, the direction of field is same as that of position vector. If you take the charge as negative, then the direction of field is opposite to the position vector. You know that the magnitude of field will be equals to kq by magnitude of r whole square, and the direction is same as that of vector r given that I take this charge as positive. First of all, let's do for positive. We will think about negative later. So you will say the electric field in vector form will be nothing but the magnitude times a unit vector in direction of vector r. So that will be kq by magnitude of r whole square into a unit vector in the direction of r. That will give you kq into vector r upon magnitude of vector r whole cube. Now bachcho, notice the beauty of this particular formula. If q is positive, yes, then electric field and r are parallel, yes. And if q is negative, then you will get a negative sign here. And that negative sign tells us that the direction of electric field and position vector are anti-parallel. So this formula is self-adjusting formula. You just have to make sure that you substitute the charge q with sign. So remember that you must substitute the charge q with sign, and this formula is self-adjusting. It works both for positive charges as well as negative charge. If you substitute here positive charge, then E becomes parallel to R. If you substitute here negative charge, then you get a minus sign. That tells you that E is anti-parallel to R. Easy? So now let's practice some questions. Determine the field due to both the masses at point O. So there are two masses, one mass here, and the separation between these two masses is d. Our mission is to write the gravitational field intensity at a point O, which is at a distance x on the perpendicular bisector. So how to write the net gravitational field at this point? Two questions to you. First, field is dash quantity, vector quantity. Second question, a mass produces field towards itself or away from it? Sir, a mass always produces field towards itself. So at this point O, the gravitational field because of the first mass will be towards it. The gravitational field due to the second mass will also be towards it. If let's say I take the strength of these two gravitational field intensity to be I and I, sir, how can you take them to be same? Because both the masses are same and their distance from point O is same. That's why I'm taking the strength of these two gravitational field intensity to be same. And let's say this angle is theta as well as this angle is theta. The answer is very easy. You will just say field is a vector quantity. So I can break down this gravitational field intensity I into component. This way I will get a component I sin theta. This way I will get a component I cos theta. Similarly, if I break the other gravitational field intensity, this way I will get I sin theta, and this way I will get I cos theta. So what will be the resultant of the gravitational field I and I produced by these two masses given that this angle is theta? So you will say I cos theta plus I cos theta, the net gravitational field intensity come out to be downward, and that is 2I cos theta. I ask you, can you write the strength of gravitational field due to one mass here? Yes, sir. How? Sir, I know the mass, I know the distance, I can write it. Can you tell me what will be this angle theta? Yes, sir. I can think of this right angle triangle. In this right angle triangle, this angle is theta, this base length is d by 2, and this length is x. So I know the three sides using the Pythagoras theorem, so I can tell you what is cos theta. Once you know what is the field strength and once you know what is cos theta, game over. You know that I resultant has to be equals to 2I cos theta. Now let's find out it in the proper value. So you will say the gravitational field due to both the masses will be towards them, and the field is a vector quantity. So when you add up field, you have to do vector addition. Now visualize that the first mass produces a field I towards it. The second mass also produces a field I towards it, and the angle made by this field strength with the perpendicular bisector is theta. So you will say that I resultant will be nothing but 2I cos theta. Now sir, how to write I and how to write cos theta? It's easy. Can you tell me what is this distance? Sir, look into the right angle triangle. This distance is x, this distance is d by 2. So this distance has to be under root of d by 2 whole square plus x square, right? You know the distance, and this angle is theta. Can you guys now tell me what is cos theta? Sir, cos theta has to be base upon hypotenuse. For this angle theta, the base is x and the hypotenuse is under root of d by 2 square plus x square. So cos theta comes out to be x upon under root of d by 2 whole square plus x square. The formula looks ugly, but it is simple to find. So you will say that I resultant will be 2 into I. Sir, how do you got this I? We know that due to a mass m at distance r, the field is nothing but gm by r square towards the mass. So here, due to a mass m at point O, the field will be gm upon distance between mass m and O whole square. The distance between mass m and O is under root of d by 2 square plus x square and then whole square it, right? Now this will be your field strength I at the point O due to one of the mass. And this whole quantity kit is your cos theta. Sir, how do you know this is cos theta? Very easy. Look at this right angle triangle. This length is x, this is d by 2, this is under root of d by 2 whole square plus x square, and this angle is theta. So cos theta is x upon under root of d by 2 whole square plus x square. Now see kids, here you have got root and whole square. So you can eliminate it and write I resultant to be equals to 2 gm upon d by 2 whole square plus x square multiplied by x upon d by 2 whole square plus x square raised to power of half. In place of root here, you can write raised to power of half. So what you get is d by 2 whole square plus x square into d by 2 whole square plus x square raised to power of half. When you multiply t into t raised to power of half, you get t raised to power of 3 by 2. No? 1 plus half gives you 3 by 2. Similarly here, d by 2 whole square plus x square raised to power of 1 into d by 2 whole square plus x square raised to power of half gives you in denominator d by 2 whole square plus x square raised to power of 3 by 2. This is a result that you should remember. So the resultant gravitational field intensity is 2 gmx upon d by 2 whole square plus x square raised to power of 3 by 2. Same type of result we will get for a ring. Rather than thinking of it this way, I recommend students to remember it as g into 2m into x upon under root of d by 2 whole square plus x square whole cube, or simply remember it as g into 2m into x upon d by 2 whole square plus x square raised to power of 3 by 2. Sir, why you have taken 2m in one place? It will become clear when I talk about the ring, but keep it in mind. So tomorrow, if rather than giving you two masses, they give you two charges, Q and ask you, what is the strength of the field at a distance x? So you will say, now you have just changed mass with charge. So here the electric field intensity will be equals to K into 2Q into x upon d by 2 whole square plus x square raised to power of 3 by 2. So easy. So let's move on and keep on understanding more about electric field with the next example. Question is, find the field at a point A due to this rod having a charge Q and length L. So there is a rod, the rod has a charge Q, the rod has a length L, and you need to determine the electric field intensity at a point A such that the closer end of the rod is at a distance r from A. So how to write the electric field at point A? You will say, to write the electric field at point A, I can think of entire charge to be placed at the center of charge, and the center of charge will be at the center of the rod. So this length will be L by 2, this length is R. So I can assume the entire charge Q to be placed at distance L by 2. So the electric field intensity will be nothing but K into Q times the distance of this point A from the center of charge upon L by 2 plus R whole square. Simple. Don't do this. This is absolutely wrong. There is no such goddammit concept as center of charge. You shouldn't take the entire charge of the body to be placed at its center of charge. There is no such concept. Luck by chance, for the case of spheres, when they have got uniform charge density, only for the case of spheres, we can assume the entire charge to be placed at the center when you are writing field for outside points. We will talk about this when I tell you how to write the field due to shell and solid sphere. But remember that there is no such goddammit concept as the center of charge. Center of charge doesn't exist. Okay, so sir, how to do it now? We know that due to a point mass m, we know how to write the gravitational field at distance r, it is gm by r square. And due to a point charge q, we know that to write the electric field at distance r, we write the electric field as kq by r square. One can think of this charged rod to be made up of infinite number of infinitely small charges. Now you can write the field at point A due to one such infinitely small charge and then integrate. So how to do it? Focus here. Go at some random distance x from A and think of an infinitely small thickness of charge. Now this infinitely small thickness is written as dx. Now do understand, I am showing here big, but you must visualize infinitely thin. So a very small thin piece. Okay. Now in this infinitely small thickness dx, how much charge will be present? So you will say, sir, the total rod has a charge q, the total rod has a length l. Our mission is to determine what will be the infinitely small charge dq in this infinitely small thickness dx. So from unitary method, we will say that the infinitely small charge dq has to be equals to total charge upon total length. That becomes the charge per unit length multiplied by the length in which we wish to write the charge. So we will say that dq equals to q by l into dx. Once you have written this dq, game over. Now you can write the field at point A because of this dq. You know that due to a charge q at distance r, the electric field is given by kq upon r square. But do understand, here your charge in consideration is infinitely small. So due to an infinitely small charge dq at distance x, what will be the field? So sir, since the field is being produced by an infinitely small charge, the field will also be infinitely small. So the infinitely small electric field produced will be k into dq upon this separation whole square x square. So you can write dE equals to k into dq upon x square. Now substitute the value of dq and you get dE equals to k into q into dx by l into x square. See, in place of dq, I have substituted q by l into dx. Now sir, what to do? Integrate. You know what is the infinitely small electric field produced by an infinitely small charge dq. You need to find the electric field produced by the whole rod. So integrate. Sir, integrating E from 0 to the total electric field. But how should I substitute the limit of x from where to where? So what is x? Sir, x is the distance from the point where we wish to write the field. Now, at which value of x the rod starts? So, sir, the rod starts when x is equals to r. And the rod ends when x is equals to r plus l. So, here we need to substitute the limit of x. So, at which value of x we should start so that the rod begins at x equals to r. And up to which value of x we should go for the rod to end? Up to x equals to L plus R. So you will substitute the limit of x from R to L plus R. Now here the integration involved is not at all tough. If you know the integration of x raised to the power of n dx, it's a simple thing. Integration of x raised to the power of n dx gives you x raised to the power of n plus 1 upon n plus 1. So here integrating both the side, you will write first, before integration, we can bring this x square from denominator into numerator and write it as x raised to the power of minus 2 dx. Now integrating both the side with proper limit, you will get integration of dE from 0 to e equals to kq by L outside. Integration of x raised to the power of minus 2 dx from lower limit r to upper limit r plus L. Now what will be the integration of x raised to the power of minus 2 dx? Sir, integration of x raised to the power of minus 2 dx will give you x raised to the power of minus 1 by minus 1. Integration of x raised to the power of n dx gives you x raised to the power of n plus 1 by n plus 1. Now this can be written as minus 1 by x. Now here understand that the lower limit is r, upper limit is r plus l. Lower limit is r, upper limit is r plus l. So you will get integrating dE, you get e equals to kq by L outside. Integration of x raised to the power of minus 2 dx gives you minus of 1 by x. Lower limit r, upper limit r plus l. always substitute upper limit minus lower limit. So first in place of x substitute r plus l, then in place of x substitute r and subtract them. So you get E equals to minus kq by l into 1 upon r plus l minus 1 upon r. So cross multiply, here you get r, here you get r plus l, and in denominator you get r plus l into r. So you get E equals to minus kq by l into minus l upon r plus l into r. The L get cancelled, the minus get cancelled, you get a plus, and hence the field comes out to be kq upon r times r plus l. Many times students ask me, sir, do you remember this result? And I say yes. How? Do you guys know that the geometric mean of two numbers a and b is root ab? So if you have got two numbers like 4 and 9, then their geometric mean is under root of 4 into 9, that is under root of 36, which is 6. This is called geometric mean. Now the two ends of this rod are at distance r and r plus l. So take the mean distance as geometric mean of two ends. Take the mean distance as the geometric mean of two ends. And the geometric mean of these two ends of rod will be under root of r into r plus l. So you can think of electric field to be simply kq by geometric mean distance whole square. Just like you write the field due to a charge q at distance r, kq by r square. Here kq upon mean distance root r into r plus l whole square. So that gives you kq upon r into r plus l. It's helpful to remember the result when you are preparing for a competitive examination like NEET, where you get 1 minute to answer one question. So let's focus on the next thing, which is null point. What is null point? Sir, null point are nothing but point of zero resultant field. In case of gravitation, they are the point where the net resultant gravitational field intensity is zero. In case of electrostatic, those are the points where the net electrostatic field intensity is zero. So if you have got two masses m1 and m2, where is the null point? We have learned yesterday, for two masses you always find the null point to be between the masses. The distance of the null point from mass m1 is root m1d upon root m1 plus root m2, and the distance of null point from mass m2 is root m2d upon root m1 plus root m2. Then I taught you guys the case of like charges is same as that of gravitation. So if you have got like charges q1 and q2, where do you find the null point? Null point means the point at which the net field is zero. If you are talking about charges, you are talking about electrostatic field to be zero. So at the null point, you will say that the net electrostatic field is zero. So if you have got two charges q1 and q2, so the case is same as that of gravitation. So the null point will be at a distance root q1d upon root q1 plus root q2 from the charge q1, and at a distance root q2d upon root q1 plus root q2 from the charge q2. If you have got unlike charges, then I taught you guys in the last hour, then the null point is found on the line joining the charges, outside the charges, closer to the charge of smaller magnitude. So if you have got unlike charges where the magnitude of q2 is less than q1, then the null point is found on the line joining the charges, outside the charges, closer to the charge of smaller magnitude, which is q2 in this case. And the distance of this null point from q2 is root q2d upon root q1 minus root q2. q1 is bigger than q2, right? So root of bigger minus root of smaller. And the distance from q1 is root q1d upon root q1 minus root q2. So you need to remember this result. This will help you answer question quicker in your NEET examination. Do remember, when you are substituting for charges, beta, please substitute only the magnitude of charge. So if let's say both the like charges are negative, let's say minus 2 coulomb and minus 4 coulomb, then do not substitute here minus 2 and minus 4. Negative of root will be a complex number. Just substitute the magnitude. So for like charges, use this, same as gravitation. For unlike charges, you will get the null point on the line joining the charges, outside the charges, closer to the charge of smaller magnitude. So keep this simple thing in mind. It's a useful thing. So moving on. So now we will talk about field due to different type of systems. First, we will talk about two particle system. If you have got two masses or you have got two charges identical, then what is the field at their perpendicular bisector. Sir, we have already derived it. Yes, so that's why we are directly going to write the result. So if you have got two masses separated by distance d and you need to write the resultant gravitational field at a distance x on its axis, then the gravitational field is given by g into 2m into x, g into 2m, total mass of system, into x upon d by 2 whole square plus x square raised to power of 3 by 2. This is the field due to two masses. Now, if you have got masses, the masses produce field toward themselves. So the resultant field at this point will be towards the center of the line joining these two masses. So this will be the direction of gravitational field. Now, if you have got two charges q and q, if both of them are positive, understand that positive charge produce field away from it. So if for this positive charge, the field will be away from it, let's say E. Due to this positive charge, the field will be away from it. So you will get the net electric field here, away. But if the charges are negative, negative charges produce field towards themselves. So if these two charges are negative, then the first charge will produce field towards itself, the second charge will produce field towards itself, and you will get the net electric field towards the center of the line joining the two charges. So here in this case, you will say the electric field intensity will be, in place of G, you will get K, in place of 2M, you will get 2Q, and rest is same. So K into 2Q into X upon D by 2 whole square plus X square raised to power of 3 by 2. Remember this case is same as that of ring. This case is same as that of ring. What is same here as that of ring? I will explain in a few moments when I start teaching about ring. So now let's think of the second case of the ring. If you have a ring of mass m and radius r, can you tell me what will be the net gravitational field intensity at the center of ring? So you are asking me the net gravitational field intensity at the center of the ring. Field intensity is a vector quantity. One can think of this whole ring to be made up of many small masses. Each mass will produce a field towards itself. And when you think of all these gravitational field vectors getting added up, what will be the resultant? So they will cancel out each other. So the simple question, what will be the gravitational field intensity at the center of this ring? 0. So the gravitational field intensity at the center of a ring with uniform mass distribution m is 0. Similarly, if you have a ring with a charge q, if the ring has got positive charge, then each small part on this ring will produce a field away from it. But if you think the field due to all the charges, then again the field will be distributed over a circle, and field is a vector quantity. When you add up all these vectors, keeping direction into consideration, the net electric field at the center becomes 0. So remember that if the charge and mass distribution is uniform, then the field at the center of the ring is 0. But they won't ask you field at the center. They will ask you what is the field at a point on the axis. So let's see that case. So what is the field due to a ring on the axis? First, let's talk about the mass. Once we know about mass, we already know about the charge. Now, I said that the case of the ring is same as that of two masses. When I did solve this same question for two masses, I said that the separation between the two masses is d, yeah, and each mass produce a field towards itself, yes. So we get the net field somewhere here, and I said that I resultant is nothing but 2I cos theta, where this angle is theta, and the field produced by each mass is I. Now here visualize that you have got mass distributed over a ring, and you are thinking of the field at a point on the axis of the ring. Now each mass on the ring will produce a field towards itself. So if you visualize the field due to each mass on the ring, then the gravitational field vector at this point will lie on a cone. Think of 3D. This is the ring. Each point on the ring produces a field on the axis towards itself. So all these gravitational field vector will form a cone, and the resultant will be towards the center of the ring. How much magnitude? Same. For two masses, we got what? Two masses m and m separated by distance d. We got the field to be equals to G into 2m into x upon d by 2 whole square plus x square raised to power of 3 by 2. Here 2m is what? Total mass of the system. D is the separation between two extreme mass. Here the separation between two extreme mass is 2r. So D is kind of 2r. So D by 2 is same as that of r. D by 2 is same as that of r. So in this case you get the gravitational field intensity to be G into total mass of the system, the total mass on the ring, m, into x. In place of d by 2 we simply substitute the radius of the ring, r square plus x square raised to power of 3 by 2. And that's why I love physics. When you remember one thing here, it helps you remember the other things as well. So remember that the two mass system and the ring are brother case. Just that in place of d by 2 you substitute r, and in place of 2m, which is the total mass in the case of two mass system, you simply substitute the mass on the entire ring. So the gravitational field intensity comes out to be gmx upon r square plus x square raised to power of 3 by 2. Now this gravitational field intensity is maximum when x equals to r by root 2. So why? See, at the center of ring, when x equals to 0, this point reaches the center of ring. At the center of ring, what is the gravitational field intensity? So we have just learned at the center of ring, the gravitational field intensity is 0. If you move at infinite distance from the ring, what will be the gravitational field intensity? So sir, at infinite distance, the distance from each mass will be very large. So the field effect due to each mass will be very small. So at infinity, again, the gravitational field intensity will be 0. So at the center of ring, the gravitational field intensity is 0. When x equals to infinite, the gravitational field intensity is 0. It means that as we move from center to infinity, the strength of gravitational field intensity first increases and then decreases. It is maximum at some distance, and that distance comes out to be r by root 2. So at what distance on the axis of the ring, the gravitational field intensity due to ring is maximum? Sir, at x equals to r by root 2. If they ask you, tell me what is the value of this maximum possible gravitational field intensity, then in place of x beta simply substitute r by root 2 and you will get the answer. So you'll get I equals to gm into r by root 2 upon r square plus r by root 2 whole square raised to power of 3 by 2. This will be the maximum possible strength of gravitational field intensity. So if we think of the graph of gravitational field intensity versus the distance on the axis, we get this type of graph. Notice that the maximum value of gravitational field intensity is at a distance r by root 2 from the center. Sir, I've got one doubt. What better? Sir, the doubt is that why for positive x you have taken the field as negative and for negative x you have taken the field as positive. Understand that for a mass it produces field towards it. If you think of the points on the axis and let's say you take this direction as positive x and this direction as negative x. At a point here, the direction of field will be towards the mass. So in the negative x, that's why we have taken the gravitational field intensity as negative for positive x. And for negative x, at this point, the field will be towards the mass. So the net field will come out towards the center of the ring, that will be towards positive x. Since for positive x, we get field in negative direction. And for negative x, we get field in the positive direction. This is the graph. And the strength of field is maximum at a distance r by root 2. The same thing can be done for even the case of charge. If you have a ring of charge q having a radius r, then at a distance x on its axis, the electric field intensity is given by kqx upon r square plus x square raised to power of 3 by 2, the same formula. Again, the electric field intensity will be maximum at the value of x equals to r by root 2. If they ask you in question, tell me what is the maximum strength of the electric field on the axis, you know that it is at x equals to r by root 2. So here in place of x substitute r by root 2, you will get the maximum possible strength of electric field. If you think of the graph of electric field strength versus the distance, you will say first the electric field strength will increase, it will be maximum at a distance r by root 2 and then it will decrease. Now notice that for electric field, for a positive value of x, I have taken electric field as positive. Why? Because I have assumed that this charge is positive. So what if they tell me that the charge on the ring is negative? Then you will get the same graph as we got for the gravitational field. Why? Because a positive charge produces field away from it, while a negative charge produces field towards it. So if they give you negative charge on ring, then draw this type of graph. If they give you positive charge on ring, then draw this type of graph. And the strength of electric field is maximum when x equals to r by root 2. Okay, so let's now move on to the next case, and now we will talk about the field due to a shell. So if you have a shell of mass m and radius r, how to write the field due to this shell at a distance r from the center of shell? Now you can think of two type of points. One, inside the shell. For any point inside the shell, the distance from the center r will be less than the radius. For such points where the distance from the center r is less than radius, the field is 0. So remember that the field due to a shell inside the shell is 0. The field due to a shell inside the shell is 0. Once more, the field due to a shell inside the shell is 0. But if you think of one point whose distance from center is greater than the radius, for such a point which is outside the shell, you can assume the entire mass of the shell to be placed at the center. So if you assume entire mass of the shell to be placed at center, a mass m, and now you have to write the gravitational field intensity at distance r, the gravitational field intensity will be simply equals to gm by r square. So remember with me, the field due to a shell inside the shell is 0. For outside point, you can assume the entire mass to be placed at center of shell. The same thing now I am going to say for charge. If you have a sphere of charge q and radius r, again you can think of two types of point, one inside the shell, one outside the shell. For the point inside the shell, the distance from the center will be less than the radius. For such a point inside the shell, the field due to the shell inside the shell is 0. If you are talking about mass, then the gravitational field intensity is 0. If you are talking about charge, then the electric field intensity is 0. The field inside the shell because of the shell is 0. For outside point, if you think of a point outside the shell such that r, the distance from center, is greater than the radius, then you can assume the entire charge of the shell to be placed at its center. So if you have got a charge q, then what will be the electric field because of it at distance r? The electric field will be equals to kq upon r square. So now remembering the important statement about shell. The field inside the shell due to shell is 0. The field inside the shell due to shell is 0. The field inside the shell due to shell is 0. For outside point, assume everything to be placed at center. If you are talking about mass, then assume the entire mass to be placed at center. If you are talking about charge, then assume the entire charge to be placed at center. Now let's see what does the graph of field with the distance from the center looks like, both in case of gravitation as well as electrostatics. So if we think of the graph, if we have a shell of mass m and radius r, how does the graph of the gravitational field intensity versus the distance on the axis looks like? So you will say from center till the surface, there is no gravitational field. At all these points, there is no gravitational field. So the field intensity is 0. For outside point, we can assume the entire mass to be placed at the center. So the strength of field keeps on decreasing as you keep on moving away and away. But sir, why you have drawn here in negative? Because beta, a mass produces field towards itself. If you take this direction as positive x, then the gravitational field will be in the opposite direction, in the negative direction. That's why drawn in negative sense. As you keep on moving away from the surface of shell, the strength of field keeps on decreasing. It keeps on becoming less in magnitude, less negative in magnitude. So you get this type of graph. And for negative x, from center till minus r, there is no gravitational field intensity at all these points. That's why 0. After minus r, at this point, the field will be towards the mass. So the field will be in positive direction. But as you keep on moving towards negative x away from the center, the strength of the field keeps on declining. So this is the graph for a shell of mass m versus the distance from its center. We can draw the same type of graph for charge. It's just that if I assume the charge to be positive, the field produced by a positive charge is away from itself. So from center till distance r, the strength of field is 0. For outside point, the field strength keeps on decreasing. For charge, I have assumed here the charge to be positive. Sir, if in the question they give me negative charge, then better draw this type of diagram. Now, as the distance keeps on increasing, the field strength keeps on decreasing. Important point, on the surface of shell, the gravitational field intensity is gm by r square. On the surface of shell with a charge q, the electric field intensity is kq by r square. So on the surface, you get the electric field intensity to be kq by r square. Inside the surface, the electric field intensity at all point is 0, and for outside point, as you keep on moving away and away, the strength of electric field keeps on decreasing. So let's move on and do a question. A charge q is placed at the center of a shell of radius r. So you have a shell with a charge q at its center, and the shell has a charge capital Q. Find the electric field at a distance r from the center of the shell. So for r less than r, somewhere here, and for r greater than r, somewhere here. So how will you write the electric field at this point for r less than r? Tell me, if I call this point which is inside the shell for r less than r as a point P, tell me at point P, we will have the field because of shell, yes or no? No. The field inside a shell because of shell is 0. But you can't say that the field inside the shell is always 0. The field can be there present inside the shell due to another charge placed inside the shell. So at this point inside the shell at distance r from the center for r less than the radius, you will get at this point the field due to the charge placed at center, but you won't get the field due to the charge on the shell. So you will say field inside the shell due to shell is 0. For outside point, assume the entire charge to be placed at center. So for r less than r, the electric field comes out to be simply kq upon r square. Why? Because for r less than r, at this point there will be no field due to the charge on the shell, but there will be a field due to this charge q placed at center, which is at a distance r. So the electric field at this point for r less than r will be equals to kq by r square. Now, how to write the field at an outside point? So sir, for outside point, this charge q will produce a field. Yes, how much? Kq by r square. This shell will produce a field. Yes, how much? Kq by r square. We can assume the entire charge of shell to be placed at center. So you can visualize for outside point as if there is already a charge q at center and the whole charge of shell also at center. So there is a charge q plus q placed at center, and now they are asking you what is the electric field at distance r. So you will say simply the electric field at distance r will be k into q plus q upon r square. So you will say for r greater than r, for some outside point, we can assume the charge at center to be at center as well as the charge of shell to be at center. So the total charge at center becomes a small q plus capital Q. So the electric field equals to k into small q plus capital Q upon r square. Easy. Now let's see one more example based on shells. So now we have got two shells. Inner shell of radius r1 having a charge q1 and outer shell of radius r2 having a charge q2. We have got these two concentric shells. Question is, two concentric shells have charge q1 and q2 and radius r1 and r2 as shown in the figure. Find the field at a distance from center r less than r1. When they say r less than r1, they are talking about a point inside the inner shell. Now if I call this point x, tell me at point x there will be field because of charge q1, q2, both none. So the field inside the shell because of shell is 0. Yes. So at the point x, which is inside both the shells, the field due to both the shells will be 0. Hence, the net electric field at the point x will be 0. If we think of a point y for which the distance from the center is greater than r1 and less than r2, so it lies between the two shells. Tell me at point y the field will be present because of q1, q2, both none. So you will say, sir, the point y is inside point for q2 but outside point for q1. So at point y there will be field because of q1 but there won't be any field because of q2. So at point y there will be field only due to charge q1. And if you think of another point z which is outside both the shells, then for point z the distance from the center is greater than the radius of the outer shell. So for such a point z you will get the field because of both q1 as well as Q2. Okay. So for point Z, you can assume the entire charge of shell 1 to be placed at center as well as entire charge of shell 2 to be placed at center. And you can write the field at point Z. So we will say for the first case, when R is less than R1, the electric field will be 0, as this point for R less than R1 is inside both the shell, and the field inside the shell because of shell is 0. So the net electric field will be 0. For the second case, when R is greater than R1 but less than R2, at this point the field because of Q2 will be 0, because this point is inside the outer shell. But at this point there will be a field due to Q1, and you can assume the entire charge of Q1 to be at center. So if you think of Q1 to be at center and this distance is R, the electric field comes out to be simply KQ1 by R square. For an outside point which is greater than R2, you can assume the entire charge Q1 to be placed at center as well as entire charge Q2 to be placed at center. So you can think that as if you have a charge Q1 plus Q2 placed at center, and they are asking you the electric field at distance R. So for R greater than R2, the electric field will be simply equals to K into Q1 plus Q2 upon R square. This is how easy questions are of multiple shell. But sir, potential questions are difficult. Do not worry. In the next to next hour, we will talk about potential questions for multiple shell. That is also easy. So now let's continue further. So now we will talk about field due to solid spheres. Now, if you have got a solid sphere of mass m and radius r, then even at some distance r from the center for r less than r, the gravitational field is not zero. So for a distance r less than r, the gravitational field intensity is given by gmr by r cube. What is g? Universal gravitational constant. What is m? The whole mass. What is r? The distance from the center. And what is r cube? The radius of the sphere whole cube. Now we treat Earth as a solid sphere. So this particular result is really important when we talk about acceleration due to gravity due to Earth. So keep this result in mind. This is a really important result. Now what I tell kids is, rather than thinking of this as gmr by r cube, always think of this as gm upon r square into small r by capital R. Why? This tells you that this is the value of gravitational field intensity on the surface, gm by r square, into small r by capital R tells you that as you go from the center to the surface, the gravitational field intensity increases linearly. If let's say today I have got 0 rupees, after 100 days I have got 1000 rupees. So how many rupees I will have after x days? So you will say, sir, in 100 days your money grows from 0 to 1000. So after x days, the number of money you will have is total money into the number of days upon total number of days. So here think that going from center to surface, the field intensity increases from 0 to gm by r square. So at the distance small r from the center, the field is given by the increase in the field intensity moving from center to the surface, gm upon r square 1000, multiplied by distance from the center upon the overall distance that has to be traveled for the field to grow from 0 to gm by r square. Now for r greater than r, for an outside point, again you can assume the entire mass to be placed at center, and the field comes out to be simply equals to gm by r square. So for outside point, it's still the same. For outside point, you can assume the entire mass to be placed at center. But in this case, since even the mass is present in bulk, even in the bulk, you don't find zero gravitational field intensity. So as we move from center to the surface, the gravitational field intensity increases linearly. Now the same thing can be said even for the case of charge. If you have got a sphere with uniform charge distribution Q, charge is distributed everywhere in the flesh. In the question, you have to be very careful that they have given a conducting solid sphere or a non-conducting solid sphere. Because as I will teach you in the lecture on conductor, in case of conductors, the entire charge is present only on the surface. Since in case of conductor, the entire charge is placed only on the surface, in case of conducting sphere with a charge Q, it is as good as a shell because the entire charge is present only on the surface. Here, I'm talking about a non-conducting uniformly charged sphere where the charge is present everywhere in the flesh. Now for such a sphere, you get the same result as that for gravitation. You will say for R less than R, the electric field intensity, in place of G, write K, in place of M, write Q, and you get KQR by RQ. Or I will again recommend to remember this as KQ by R square into small r by capital R. For r greater than r, for an outside point, you can assume the entire charge to be placed at center and you simply get the electric field intensity to be kq upon r square. This particular linear growth case is taught at three places in physics. One for solid sphere, or you can say for the case of Earth. One for a charged sphere having uniform charge distribution in its volume. And once I will again teach you the same type of thing in magnetism. In the NEET 2019 paper, all three questions came. On which thing? On the linear growth. So that's why this linear growth case is really important. Stay focused to this. So now listen to this. Moving from center to the surface, the field increases linearly. Moving from center to the surface, the field increases linearly. So if on the surface the field intensity is I, then at a distance r by 2 the field intensity will be I by 2. At a distance r by 3 the field intensity will be I by 3. So going from center to surface, the field intensity increases linearly. For the outside point, the entire thing can be assumed at center. For the case of mass, you can assume the entire mass to be placed at center. For the case of charge, you can assume the entire charge to be placed at center. So moving from center to surface, the field increases linearly. For outside point, assume the entire thing to be placed at center. Such an easy thing. So now we will talk about the graphs. So for the case of solid sphere having some mass m, how do we write the gravitational field intensity variation with the distance? So going from center to the surface, the gravitational field intensity increases linearly. And then for the outside point, you can assume the entire mass to be placed at center. So as you keep on moving away and away and away, the field strength keeps on decreasing. Sir, why are you again drawing negative beta? Simply because if you think for positive x, the field direction will be towards the mass. A mass produces field towards itself. That's why I have drawn it as negative. The value of field strength on the surface for distance from the center equals to r will be nothing but gm by r square. This question is asked, where is the magnitude of field strength due to a sphere of mass m and radius r is highest? So you will say the field strength is maximum on its surface. As you move from center to surface, the field strength linearly increases and then it decreases. So the field strength due to a sphere of mass m and radius r is maximum on its surface equals to gm upon r square. I will use the same result when I teach you the acceleration due to gravity. So keep this result in mind. This is important. Similarly, if you have a sphere with a charge q and radius r and they have given this is a non-conducting sphere, because for conducting sphere entire charge is present on the surface, it is as good as shell. If they have given a non-conducting sphere where the charge is distributed over the flesh, then you say that again moving from center to surface the field increases linearly, and for outside point it decreases. The electric field due to a non-conducting uniformly charged solid sphere is maximum on its surface, and this field strength comes out to be equals to kq by r square. So inside it is less than kq by r square, outside it is less than kq by r square. It is maximum at the surface equals to kq by r square. Keep this in mind. Now we will talk about the line system. If you have got infinitely long line mass, or if you have got infinitely long line charge, then what is the gravitational field and electric field because of them? So if you have got infinitely long line mass having mass per unit length lambda, then you say that the gravitational field intensity because of it at distance r is given by 2g lambda by r. 2g lambda by r. 2g lambda by r. Remember it. So if you have got an infinitely long line mass, then because of this line mass having mass per unit length lambda, the gravitational field at distance r is given by 2g lambda by r. And this mass produces a gravitational field towards itself. Why? Because masses produce field towards themselves. So when you think of the resultant field due to all the masses, you get the net gravitational field towards the mass, where lambda is the mass per unit length here. Okay. Now, similarly, if you have got an infinitely long line charge, if this is a positive line charge, then it will produce electric field away from it. If it is a negative line charge, then it will produce electric field towards it. Due to this infinitely long line charge, the electric field intensity will be, in place of G, you will get K, and in place of lambda, which is mass per unit length, you will get charge per unit length, and the same distance R. So the electric field intensity comes out to be 2K lambda by R. Here, lambda is nothing but the charge per unit length, and for mass, here lambda is mass per unit length. So you can remember one of them, and remembering the other one becomes easy. Now, if you have got case of half ring, if you have a half ring of mass m, so if you have this half ring, for complete ring, we know that what is the gravitational field intensity at center. So for complete ring, each mass produces field towards itself. For a complete ring, the gravitational field intensity at center is 0. But if you do not have a complete ring, you have a half ring. Now, if I ask you what is the gravitational field intensity at center, so if you think of this half ring to be made up of many small masses, okay, then each mass will produce a gravitational field towards itself. Now, the resultant of all these gravitational field intensities won't be 0. Because of symmetry, they will come out to be somewhere here. Now, sir, how much is the magnitude? If you have remembered the formula for the gravitational field intensity due to infinitely long line mass to be equals to 2g lambda by r, this is the same formula. So the gravitational field intensity due to a half ring having mass per unit length lambda and having a radius r is nothing but I equals to 2g lambda by r. Now, this result you can say is same as that for an infinitely long line mass. Similarly, if you have got a half ring having a charge per unit length lambda and a radius r, if it is positively charged, then the electric field will be away from it. If it is negatively charged, then the electric field will be towards it, right? Now, the strength of this electric field comes out to be simply equals to 2k lambda by r. Here, r is the radius of this half ring, lambda is the charge per unit length. It is easy to remember because the same result as field due to infinitely long system. So keep these two results in mind as well. Now, moving on to a question. If you have got two long line charges having charge per unit length lambda 1 and lambda 2, question is, if two infinitely long line charges are separated by distance t, determine the force per unit length due to one line charge on another. So what will be the force of repulsion or attraction between these two line charges? Sir, if lambda 1 and lambda 2 are of same nature, then definitely these two line charges will repel. If the charge per unit length will be of opposite nature, one of them is positive, one of them is negative, then they will attract. Now, question is, what is the force per unit length due to one line charge on another? So think of a length L on the second line charge. At the very beginning of electric field, I said that the first charge produces an electric field at the position of second charge, and because of that electric field, the second charge experiences a force. At all these points on the second wire, we will say that the first wire produces an electric field, and the strength of this electric field is given by 2k lambda 1 by r. So we know what is the strength of electric field, and in a length L of the second wire, we know that the charge will be lambda to L. So we know what is the charge, we know what is the strength of electric field, we can write the force. So we will say that the force will be equals to the charge multiplied by the electric field. The charge in a length L, if the charge per unit length is lambda 2, then in a length L, the charge will be lambda 2 into L. And the electric field produced by first charge at the position of second charge will be 2k lambda 1 by r. So we get the force equals to lambda 2 into L into 2k lambda 1 by r. So you will get the force per unit length to be equals to 2k lambda 1 lambda 2 by r. So this is a simple result yet important result. This has came many a time, sometimes for charges, sometimes for current carrying wires in the paper of need. So this is a simple result but yet important result. So let's move on to the final thing that we need to learn about electric field, and this is the electric field due to infinitely large plates. So if you have got an infinitely large plate with positive charge, a positively charged infinitely large plate. Now see here, I have drawn finitely large plate and we are looking from the side, but you must think of an infinitely large plate. So if we have got an infinitely large plate with positive charge, for a positively charged plate, the electric field is away from it. It means that at a point on the left of it, the electric field will be towards left, and at a point on the right of it, the electric field will be towards right. A positively charged plate will produce electric field away from it. Similarly, if you have a negatively charged plate, a negatively charged plate will produce electric field towards it. So for a negatively charged plate, the field is towards it. So at a point on the left of it, the field will be towards right, and at a point on the right of it, the field will be towards left. So this is first thing you should know. Second thing, you should know the formula. What is the electric field strength due to the charge on an infinitely large plate? So if the charge per unit area is given by sigma, the charge per unit area is given by sigma, then the electric field strength is given by sigma upon 2 epsilon naught. Sir, even for line charge you did not tell how do we get 2k lambda by r. Even for this thing you did not tell how are we getting sigma by 2 epsilon naught. Even for a sphere you did not tell how we get that k q r by r cube and kq by r square for outside point. All these derivations are important and you should know them because they come under the heading of application of Gauss law and they will be taught when I teach you Gauss law. But as of now, beta, our focus is on remembering the formula. So if you have a single sheet, infinitely large sheet, having charge per unit area sigma, then the electric field is given by sigma upon 2 epsilon naught. Sigma upon 2 epsilon naught. Now, bachcho, if notice here, the electric field intensity is independent of r. That is, it is independent from the distance from the sheet. So if you have an infinitely large sheet, think 3D, infinitely large sheet. So if I ask you at point A or at point B, where the electric field strength is higher, you will say, sir, they will be same. Why? Because the electric field strength produced by an infinitely large sheet is independent from the distance from the sheet. It is simply equals to sigma upon 2 epsilon naught. But sir, in our book it is given as sigma by epsilon naught. There is a difference between conducting and non-conducting. Right now just focus on what I am saying. Everything will be clear before I complete this electrostatics, because these results will be used a lot when we understand the topic of capacitor. So just remember, as I am saying, if you have got an infinitely large sheet, then the electric field because of it is given by sigma by 2 epsilon naught. So let's practice two questions based on this. The first question, find the field at point ABC. Here you can see we have got two sheets. The first one of charge density sigma, the second one of charge density 2 sigma. You need to determine the electric field at point A, B and C. Assume both the sheets to be positively charged. Tell me at point A, the field because of first sheet will be away from it towards left. Due to second sheet will be away from it towards left. So you will say at point A, the field is towards left due to both the plates. As due to both the plates, the field is in same direction, you can simply add up the vector. So you will say the electric field at point A will be equal to the field due to the first plate. Due to a plate having charge per unit area sigma, the electric field is given by sigma by 2 epsilon naught. So because of this plate of charge per unit area sigma, the field will be sigma by 2 epsilon naught, and because of this second plate of charge per unit area 2 sigma, the field will be 2 sigma by 2 epsilon naught. So electric field at point A comes out to be sigma by 2 epsilon naught plus 2 sigma by 2 epsilon naught. That comes out to be 3 sigma by 2 epsilon naught. So this will be the electric field at point A, and this field will be towards left. Now, what will be the electric field at point B? Now see, if you assume that both the charge sigma and 2 sigma are positive, positively charged plates produce field away from themselves. So because of the plate with sigma charge density, the field will be towards right. Because of the plate of 2 sigma charge per unit area, the field will be towards left. But definitely this field strength will be higher. So you will get a net field at point B towards left. Why? Because here the charge per unit area is double. So you will say at point B, the field due to the left plate is towards right. and the field due to the right plate is towards left. Yes. So you will say the net electric field at point B will be equals to the field due to the right plate, which is stronger, minus the field due to the left plate, which is comparatively weaker. So you get 2 sigma by 2 epsilon naught minus sigma by 2 epsilon naught, and that comes out to be sigma by 2 epsilon naught, and the direction will be towards left. Why? Because this 2 sigma has got more charge per unit area. At point C, both the positively charged plates will produce field away from them. So at point C, due to both, the field will be towards right. Since due to both the plates, the field will be towards right, you will say the electric field at point C will be simply sigma by 2 epsilon naught plus 2 sigma by 2 epsilon naught. That becomes 3 sigma by 2 epsilon naught. Easy. Let's talk more with one more example. Now you have got two plates. The first plate has charge per unit area plus sigma, and the second plate has charge per unit area minus sigma. Question is, find the field at point ABC. So at the point A, the positively charged plate will produce field away from it, while the negatively charged plate will produce field towards it. As both the plates have same magnitude of charge per unit area, the strength of both the fields will be same, and hence the net field at point A will be 0. So you'll say at point A, the field due to both the plate is equal and opposite. Sir, but the point A is closer to the positive plate now and away from the negative plate now. Yes, you are right. But do understand, the field due to an infinitely large plate is independent of distance. So distance doesn't matter. If the charge per unit area is equal and opposite, the field at point A due to both of them will be equal and opposite. Hence, you will say the net electric field at point A will be 0. Now, as we talk about point B, at point B, the field due to the left plate will be away from it towards right. And the field due to right plate, which is negative, will be towards it. That is again towards right. So at point B, the field due to both the plate, the left plate as well as right plate, is towards right. Because of both of them, it is towards right. Hence you will say the electric field at point B will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, and that becomes equals to sigma by epsilon naught. Here we have just written the magnitude of vectors. We already know that both the vectors are in same direction. So you simply get sigma by epsilon naught. Now at point C, due to the positive plate, the field will be away. Due to the negative plate, the field will be towards. As they have got the same magnitude of charge per unit area, the field strength will be same, and hence the net electric field at C will be 0. So that's all in this hour where we have talked about field. Now here some properties of electric field lines are left out, which I will cover in the next hour. See you guys in the next hour where we will learn about potential and potential energy. Bye bye. So that's all for now. See you guys in the next hour.